All right, now we get back to the business of doing statistics. So, in order for you to understand any statistic that you will ever, any statistical procedure that you will ever come across, you have to understand some fundamental basics of what we call sampling theory. And the idea behind sampling theory is that out there in the broader world, there is a population that you're interested in sampling. And in a strict sense, a statistical population is the total set of observations about which you want to draw inferences. So, for example, you could be interested, if you were a researcher in the auto industry, you could be interested in miles per gallon. And you might want to know, how do different car makers, Toyota, Ford, Chrysler, etc., how do these different automakers, how do their fleets of cars that they produce vary in terms of the number of miles they get per gallon of gasoline? So if that's what you're interested in, your statistical population is the miles per gallon of every car that's currently being produced. Every car on the planet, regardless of make, regardless of model, regardless of manufacturer, that equals up to tons and tons and tons and tons of cars. If you want to know if different automakers have fleets that they produce, if you want to know if they have different mile per gallon, all you have to do is gather up all the cars in the world, put them on a set track, drive them at a set speed, record their number of gallons that they consume over whatever the mileage of the course is, and you would have the answer. Assuming that you can gather up all the cars in the world and measure mile per gallon without error, you would just know the answer. If you add it up and average it, and those averages are different, they're different. They're different because you've gathered the entire population about which you're interested in. Because you are a hegemonic god and you can measure miles per gallon on all the cars that exist on the planet. Why can we not do that? You're not a hegemonic god. You can't gather up all the cars on the planet. There are too many of them. They're scattered all over the place. Even if you could, you wouldn't be able to test each of those cars exactly the same way because we're all humans. Although if you're a hegemonic god, I guess you could be perfect. And so the reason that we need statistics is that we can never access the entire population and we can never measure things without error. We all make mistakes. Our measuring instruments are only so precise. If we measured this room from one wall to another, and each of you measured it, you would all end up with slightly different measurements, even though in theory the wall is exactly the same distance apart because of measurement error. So there are a number of different kinds of errors that one can make when doing science of any kind. One of which is just measurement error. Same individual can measure the same thing 3 times and they will come up with slightly different answers. Multiple individuals measuring the same thing will come up with slightly different answers. So measurement error is one source of error. So even if you were a hegemonic god and you could gather up all the cars and measure their miles per gallon, chances are there would be variation due to measurement error. But because we don't have control over all the cars in the world, how could we get at this issue of what's the mile per gallon among different manufacturers of automobiles? Because you're not a hegemonic guy, because you can't gather up all the cars on the planet. How would you get at this thing that you're interested in? What are the miles per gallon among different automakers? The EPA does this all the time. The EPA publishes miles per gallon for different cars. You go to the car lot, it's posted there on the window sticker. How do they get those estimates? Yeah, they test them. Do they test every car that comes off the Ford line? Why not? They don't have the time. They don't have the money. Plus, Ford doesn't want you driving every car that comes off the line. They want to sell those cars with low mileage as new cars. So what do? They take a sample. And the whole idea of sampling theory is that by taking a sample, you gain some insight as to what the population is like. So rather than testing, all the cars that come off the Ford line down in Clay Como here, they take a small sample of those, they test those, and then they have a sample that they can use to make inferences about the broader population of that particular model of car. And you could go to the Ford plant, the Toyota plant, the Kia plant, the Chevrolet plant, whatever, gather up samples of the different makes and models of cars and test a small number of them. And hopefully that sample of the small number of them has some relevance to this broader population. And this is why sampling theory becomes important. Because we need to have a way of knowing that the information in our sample has something to do with the population that we're drawing that sample from. So there's a big population of cars with mile per gallon that we can observe. We're not going to access that whole population. We're going to draw a sample from that population, and hopefully that sample tells us something about the population we drew it from. The point of the card drawing exercise was to illustrate to you how this works. So in the card drawing exercise, we took a population of cards, ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, 11, 12, 13. We assigned numerical numbers to all of the cards, including the face cards that don't have numbers. And there are 4 suits of each of these. There is spade, club, heart, and diamond. So there are 52 cards, but each numerical card is represented 4 times. You have 4 aces, you have 4 twos, you have 4 threes, 4 fours, 4 kings. So if we plotted frequency of cards in a deck of cards versus their value, each of these has 4 representatives. So if we made a bar graph of it, it would look like this. And if I could draw, these would all be the same height. This, as I forget who said it last time, this is a uniform distribution. Okay? Uniform distribution just means that all of the members of the population are represented equally in that population. But then what I did is I had you draw 2 cards out of this, 4 plus 10, and take their average, 14 divided by 2. Their average is 7 in this case. Throw those cards back in, have you draw 2 more out, 3 and 12. 15 divided by 2 is 7.5. You could have drawn 2 aces, in which case the average would be 1 plus 1 is 2 divided by 2 is 1. You could have drawn 2 kings, 13 and 13 is 26 divided by 2 is 13. But your odds of drawing 2 aces are fairly low because chances are you're going to draw an ace and a 7 or something like that. And so what we find generally is if we do this over and over again, the individual averages bop around quite a lot. They fluctuate quite a lot from one two-card draw to another two-card draw. But if we take all of those two-card draws, which represent a bunch of individual samples taken from the population, we calculate that mean, we save all those. If we look at that average, the average of that distribution, a magical thing happens, which is that that distribution of the values of two-card draws is going to be normally distributed if you take enough of them. And the average of that distribution of two-card draws is going to be the population average, or pretty close to it. Well, what is the population average? Well, it's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11 plus 12 plus 13 divided by the 13 values, which the population average is 7. So in this uniform population, we should expect the average to be an average of 7 because that's the average of the population. And we know that is the average of the population because we have a small population that we're dealing with where we can measure that. So I drew two sets of cards, two samples of two cards from this population. One sample was 7, one sample was 7.5. I mentioned another one that could be 1, another one that could be 13. These are going to be more uncommon because you have to get 2 aces or 2 kings. They're at the uncommon tails of this distribution. Any other combination of things, an ace and an 8, that's 9 divided by 2 is 4.5. So you get an ace and an 8. 9 divided by 2 is 4.5. But we could also get 4.5 by drawing a 6 and a 3. We could get a 4.5 by drawing a 4 and a 5, etc., etc. So in the middle of this distribution, the observations of the means of the two-card draws are clustered, and they're clustered around the population mean. This is basically what the central limit theorem says. Any distribution, regardless of the shape, can be uniform, it can be skewed, it can be skewed this way, skewed right, skewed left, doesn't matter. It can be bimodal, it can be crazy. Draw samples from those populations. Calculate the means of those samples. Save those means, plot those means in a frequency histogram. It will start to look like a normal curve, as if by magic. But it has to do with this clustering tendency of distribution such that to get really extreme values, you had to have randomly selected members of your sample that are in one tail or the other tail. And so things tend to cluster around the middle. So that's how the central theorem works, central limit theorem works. The reason that normality matters, and this is the only reason that normality matters, is because of something called the empirical rule. I'm just going to erase this. The empirical rule just deals with normal distributions. If you have a normal distribution with an average value of this, it tends to fall off in a bell-shaped sort of shape. What the empirical rule says is that in this distribution, if you go out 1 standard deviation from the mean, 68% approximately of all of the observations in that distribution will fall within 1 plus or minus 1 standard deviation of the mean. Go out to 1.96 standard deviations of the mean, and now 95% of the observations fall between plus 1.96 and minus 1.96 standard deviations of the mean. And if you go out to 3 standard deviations of the mean, something like 99.7% of the observations fall within those 2 values. This is just the shape of a normal curve. So the empirical rule tells us that if we have a normal distribution, we know certain characteristics about that normal distribution. If we know characteristics about that normal distribution, if that normal distribution is a distribution of sample means, then we know some things about sample means drawn from a particular population. This distribution of sample means came from maybe a uniform population. So when we do statistics, it doesn't matter what the original population looks like. What matters is when we draw samples out of that population, that distribution of sample means is normally distributed. When that distribution of sample means is normally distributed, then we know something about the population of sample means that came from this original raw population. Because when we draw out a sample mean, what we're basically doing is we're estimating something. We're trying to estimate what the population mean is, but we suck at that because of sampling error. Sampling error is different from measurement error. Because when you sample from a population, you don't have access to the complete population. That's the whole point of sampling. You randomly bop around within the population in terms of your sampling. And that randomness leads to variation. And when we talk about error in statistics, don't think about error as we talk about concepts in statistics as you've done something wrong. Error is just the statistical way of talking about variation. So sampling error leads to variation in the sample means that you get from the population, not because you've done something wrong, simply because you don't have access to the entire population. If we had access to the entire population, we wouldn't need a statistics course. We would just sample the whole damn population. We calculate the average of that, and that's the average. And there's no variation around it because we sampled the entire population. If we have access to the entire population, every time we measure that population, we'll get what? Will the answer vary? No, it'll remain the same time and time and time and time again, which is why if you have access to the population, we don't have to think about sampling theory. We just measure the whole population. And then if we go and measure it a second time, we'll get exactly the same answer. If we measure it a third time, we'll get the same answer. What's the point? Measure it once, measure the whole population, be done with it. If I want to know what college student SAT scores are, I could go and grab 15 of you and ask you what your SAT scores were, and I could generate an estimate. But that would once again be a sample based on a population. We have what, 800 students on Joule? Could we get everybody's SAT scores? Oh yeah, we could. I mean, I couldn't. I mean, I guess I could ask the registrar to strip the personal information from the records and they might give me all the SAT scores. And then, if my population of interest was students at William Jewell College, SAT scores, I'd have the population. I would know the answer. If I could do that at another small liberal arts college that had a tractable population, I could get all of theirs, and I could then have the population mean of one population, the population mean of another population. And if those two numbers are different, those two numbers are different. Because there's no sampling error around those two numbers. I've got the whole population. On the other hand, if my population of interest isn't the SAT scores of William Jewell College students, even grabbing all of the SAT scores from William Jewell College, that is still just an estimate of this broader population, which is all college students. That would constitute a sample. It would be a big sample. It would be a sample of 800. But it was still just an estimate because some schools are going to have higher SAT averages. Some schools are going to have lower SAT averages because that's just a sample from this broader population. Now, if we did that across a bunch of different colleges, we could get the averages for each college, put them into a distribution, and it would start to look like a normal curve when we got enough of them. Once we know that, we can use the empirical rule to say, well, if we have a distribution of sample means, and I go and grab one sample, that sample might occur here. Another sample might occur over here. Another sample might occur very close to the population mean. But 95% of the sample means will fall between here and here. And once I know that, I can then figure out, oh, one school had a mean SAT score that was way over here. That's a pretty extreme value. It's not a value that you would expect to encounter very often. And now you can begin to put confidence intervals around your estimates of your means based on the empirical rule to say, well, this mean has an associated amount of variation around it. Therefore, when we look at this mean and compare it to another mean, if that mean is relatively close to the first mean, we can say that those two were drawn from the same population. As that mean gets further and further away from the first mean, the second mean gets further and further away from the first mean, then we have less and less confidence that that second mean came from the same population as the first mean. That's when we begin to start making decisions about whether two means came from the same population or whether they were likely to come from different populations. So we're using the empirical rule to make statements about a distribution of sample means so that we can make inferences about the population that those sample means came from. Does that make sense? If you understand that, there's no statistical test you cannot do. There's no statistical test you cannot understand. I'm going to show you this again later, but I'll show it to you now. Well, no, I won't because it's not in here. Where is it? Let's just go find it. What the heck did I do with that? I wasn't planning on doing this today. there it is. I already had a PowerPoint for it. So I'm a biologist, but I'm not a molecular biologist by any stretch of the imagination. Um, so I won't test you over this because it's not really that important except to illustrate kind of my own ignorance and how I think through things. Um, so I'm not a genomic scientist. I'm an ecologist, but occasionally there are things that I might want to do genomically to look at genetic data at a genome-wide level to ask ecological sorts of questions. And quite frankly, I find the genomic literature hard to wrap my head around sometimes. But what happens when you do a genomic study is you gather some data at a genome level, you try and sequence the entire genome of an organism, and then you basically calculate what are called LOD scores. LOD scores are basically scores that kind of give you a logarithmic idea of how likely it is that a particular genetic variant would occur. And you can test these things to see if certain regions of the genome are significantly more abundant or less abundant than other sections of the genome in terms of different variants. And I never really understood how this worked. So you have a bunch of genetic variants, and you can calculate and see, well, how different are these? They have high LOD scores or low LOD scores. And I never really understand how you could make statistical inferences about these things, because a lot of times you just see the squiggly line in a publication. But if you take these values of FST, for example, and you push them all to this side, and you just look at how frequently are their intermediate FST scores, how frequently are there extremely high or extremely low FST scores. If you compress those all to one side, it ends up conforming to a normal distribution. So even though I didn't understand exactly what statisticians were doing when they look at genomic data, I stumbled across this figure in a paper written by a genomicist who evidently thinks about data kind of in the same way that I do. And he provided this really useful graphic that allowed me to wrap my head around. That's how they can do statistical inference. Because if you take all of the individual values of FST across the entire length of the genome, squish them all into a single distribution, that single distribution is just this thing laying on its side. So when I tell you, if you embrace the central limit theorem and the empirical rule, there's no statistical method that you can't eventually understand. It may take a little bit of work to understand it, but it's the same underlying concept. We're going to be revisiting it every day for the rest of the semester. Okay, so if you can get this down, you're a long way towards being there. If you can't get this down, there is no hope for you in understanding virtually everything else we're going to be doing. This applies to sample means. When we do regressions where you look at the relationship between a y variable and an x variable, there's a distribution of slopes that behaves the same way. So when we make inferences about the slope, we're once again invoking the central limit theorem and the empirical rule. It's just that now it's a distribution of slopes rather than a distribution of sample means. In many ways, the slope is the sample mean of y as x varies. And we'll talk about that when we get to regression. So this is possibly the most important day in this class. All right, questions before we go on? All right, if you haven't already, um, install package rmisc. These instructions were on the board earlier, but then I erased them. And then once you've installed that package, load it up using the library command. And then once we have that, we will move on. Does everybody have their sticky notes? Anybody need sticky notes? So, install packages. These are the things we'll be using today. And I always put periods at the end of these. Don't put periods at the end of these. You're already loaded up. Anybody else need sticky notes? Okay, cool. All right, put your green note up when you've got these packages loaded. That should do it. Just run that line. Yeah. It's gonna take a minute. There you go. You wait for the command prompt to come back. Now run library rmisc. To load. Yeah, but it's giving you the command prompt back. Also, you can go over here, look at packages. Scroll down to where rmisc would be. They're alphabetical. Yeah, so it's loaded. So keep in mind that anytime you run a line of code and you get the command prompt back, it's done what you asked it to do without error. Now, caveat, sometimes it does what it does and doesn't give you an error code, but it didn't do what you wanted it to do. So I have a habit whenever I'm doing coding where I'll generally ask the computer to do something for me, and then the next thing that I do is I check to make sure that it actually did it. I'm always happy when I don't get an error code, but there are plenty of times when you ask R to do something, it executes the command, but you mess something up such that it allowed the command to execute, but it didn't produce the output that you thought it was going to produce. So get in the habit of working into your code checks. Okay, I asked it to do something. Did it do it? Did it do it correctly? So that's what we're going to practice doing today also. So today, I was having you simulate this idea of sampling from a population with a single deck of cards. Low numbers of draws, few numbers of times. A computer allows us to draw any cards we want, any number of times. And then we can also make better graphs, quicker graphs, etc. So what we're going to do is we're going to just simulate what you did with a deck of cards, only we're going to do it on the computer, and we're going to do it on steroids. So here we go. So the first thing we want to do is create a pack of cards. So I create a little comment line for myself so I know what I'm doing. You'll also notice that I've put 4 dashes after it. When I put 4 dashes, 1, 2, 3, 4, when you create the 4th dash, it puts a little drop-down arrow here, and it adds a subheading in your script. As you get longer and longer and more complicated scripts, finding your way through the script is going to become more necessary, more important. And by doing this 4 dashes at the end, it allows you to take whatever is after that and you can collapse it. And if you want to see what's in there, just click there and it will expand it. So let's make ourselves a deck of cards. So we're going to make an object, assign it something, and in this case we're going to just concatenate a deck of cards. So what this is basically saying is I want to create a new object. I want to assign to this object a string of digits. C means combine or concatenate. Run that line of code. Hopefully it ran. If it ran, it should tell you what you just did, which is you created a string of 1 to 13. Woo! So exciting. You can check that it actually did that by asking it to give you card. And it gives you card. So now we're going to write a function. This is going to be your first, maybe it's going to be your first R function, I'm not sure. So we're going to make a function, we're going to call it draw. And this is a function that we're going to run on card. And then the open squiggly brackets is what you want next. And we're going to do trials. So we're going to have trial 1. Two less than signs and a hash mark. It's another type of assignment operator. We're going to ask it to draw from card. Oh, sorry. And ask it to sample card. And we're going to ask it to sample two items from card. And then we're going to replace those things in card. And in this case, the replacement doesn't matter. It would if you were doing an iterative thing. We're going to force the iteration by just doing some sloppy coding, actually. Now, this does one trial. So if we ran this, it would just give us one sample of 2 cards. And that's fine. But the whole point of this is we want to do this a bunch of times. So what we can do is we can just copy this first line and run it, 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 and run it. And so this will be trial 1, trial 2, trial 3, trial 4, trial 5, trial 6, trial 7, trial 8, trial 9, and trial 10. Okay? So I know what you're probably thinking to yourself. Dr. Kowalski, you're just doing on a computer what we already did. In our assignment, we already drew 2 cards from a deck of cards 10 times. But that's okay. Hang with me for a few minutes. We're going to take the results of that and we're going to put it in a thing called result. So once again, this special assignment operator within a function. rbind simply means that you're combining the rows together into a single element. So each time you run trial 1, trial 2, trial 3, trial 4, trial 5, trial 6, trial 7, trial 8, trial 9, trial 10, each of those goes as a single element. But what rbind is asking it to do is to put each of those things into a row within a larger matrix. And we're going to rbind all the trials. And for readability's sake, you can make this go across lines if you want. Just put a comma at the end of the line before you hit return. Oh, and I did that wrong. So one of the things that you'll notice is sometimes you get little red dots out here in the gray area. That's usually a signal that you've typed something wrong. You're typing in some scripting language that R doesn't recognize. So even before you try and run this thing, you you know that you've made some mistakes, and so try and fix those before you try and go and execute this thing. Yeah. Oh my gosh, I have a dot. I need to put dots in all my stuff, don't I? Yeah. So always syntax is important. I did it for 4. I don't know why I didn't do it with everybody else. If you were to run this, it would have given you a big nasty error message saying I can't find trial 1 without the dot because I didn't tell it trial 1 with the dot up here. So make sure that everything matches up. This will become a recurring theme today. Everything has to match. It'll become a huge ass headache by the end of the day today if it doesn't match. So highlight that whole thing all the way down to the squiggly bracket and execute that. And hopefully you will get the command prompt. If you don't get a command prompt, you're probably getting an error message. So when you have executed it and have the command prompt, put your green sticky up. If you didn't get it to work, put your red sticky up. Red sticky is up. Oh, the command prompt is just that thing right there.
Okay.
Yeah, that's the command prompt. This is the command prompt. This is what you hope to see after every thing that you run. It runs it. It may give you output, but after it gives you output, it should send you back to the command prompt. Do tab command or tab complete. So one of the things you can do is if you get part of something done, let's just skip out it. Tab, and then what are you doing now? Trial.
10.
Yeah. So one of the things that will save you some typing time is tab complete. If you start typing something that R has already been exposed to, hit tab. It'll give you a little drop-down menu of things to choose from that begin with that, and you can just scroll down the list and choose it. So for example, the next thing that I'm going to do here is, and it does it automatically for you actually, so you can just tab and it will complete it. Now it's not totally complete because you have to put something in there. Do you have it now? Blaine, did you run it and it worked? Yeah, seemed to work. Okay. So take off your green stickies. So if I type in DRA, it will drop down, or drop up in this case, a menu of things that are possible. And you can just scroll down to whichever one. If you want draw key ab line, just click tab and it will complete it. We don't want draw key ab line because that's not what we're doing, but we do want draw. And we want it to draw, which is the function that we just built, and we want it to draw from the object card. Execute that. And what you should see down in your console is you should see trial 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The first draw from the deck, the second draw from the deck. By saying replace equals true, it gives you the possibility of drawing the same card twice. Like in this case, we drew 2 3s. But that's what the replace equals true means. Yeah.
Oh, that's why.
Oh, yeah. Once again, being consistent.
Yeah. That'll change a lot. Just change that to actually.
Now you're going to have to run that whole thing again above and then run run the function itself. To work? Everybody get this to work? Produce this output? Now this also illustrates something to you that's important for you to always remember. The way R keeps track of data is by row first, column second. And so when you see this notation here, what it's basically saying is that you're at the top of column 1 and all the rows are there. You're at the top of column 2 and all the rows are there. This is a blank spot. So whenever you want to reference something within a data frame, you can reference it by row and column if you want to reference an element. So this is all the rows in column 1, all the rows in column 2. Now we asked it in our function to save this as a result as part of that function. So we can see if it actually did that by just typing result. And it should produce the same thing that we just saw. Okay, so it has not only done the drawing of the cards, but it has placed it in result. Do you guys get the same actual numbers as me? No, you got different ones. Okay, good, because it should be drawing randomly. So the unfortunate thing is that this little matrix isn't in a form that's easily manipulatable. And so what we want to do is we wanted to convert it into what R refers to as a data frame, which is just the common structure within R that it uses to organize data. Right now it's just a raw matrix of numbers. And so what we want to do is we want to convert it to a data frame. So it's really easy to convert things to a data frame. Just rename it the same name that you had before and type in as.data.frame. And then the thing that you want to convert to a data frame goes in the parentheses. And when you do that, it should run without error. And if you want to see if it did it, you can get the structure of the data frame. And when you type in structure results, str result, it tells you what's in the data frame. And it tells you that it is a data frame, 10 observations of 2 variables, and these are the actual observations. So str is really useful for checking your data to see if when you did a data manipulation, did it do the data manipulation that you wanted it to do? Yeah.
It gave me this, and so that saved as the data frame.
So let's just go back up. Let's redo the draw. And that's what you got for your result. That looks exactly what it's supposed to look like. That's weird. Yeah. I don't know why that did. Sometimes just going back up and rerunning something. Oh, wait. Oh, you ran structure twice. That's what's going on. So you got the same output twice. Yeah, that's the reason. Yep. You must have just accidentally hit return twice when you did that. So now we have it as a data frame. What was it before? Let's redo the draw. And before you go to result, get the structure of draw. See, draw is a function. Then do result, and now get the structure of result before we convert it to a data frame. It's just a numeric string of numbers. So you see NUM, it's just a numeric string of numbers. It has a list of dimension names, but it's not really structured as a data frame. So then we convert it to a data frame so it has nice structure that we can look at. So what we want to do, because the central limit theorem says if you draw samples from a population, take the average of those samples, that distribution of sample means will be normally distributed. So we need to get sample means out of this. So the way we can do that is whenever you want to make a new column in a data frame, you need the data frame name, then the $, and then whatever your new column is going to be. And then you use the assignment operator to do that. And we can do this with, oh wait, before we do this, skip that. Let's rename some things so that things are easier for us. So go names, results. We're going to assign column names. You want to use the concatenate command, and we want the first one to be draw 1, and we want the second one to be draw 2. And, oh yeah, so that's giving me. So now we can once again do structure of result. And when we look at structure of result, these things are now not called variable 1 and variable 2. They're called draw 1 and draw 2. This just makes it easier to do the thing that we're about to do, which is we're about to do some math. What we want to do is we want to take result, draw 1, plus result, draw 2, and we want to divide that by 2, and that will give us the average. So what we're essentially saying is go to the result data frame, get draw 1, add it to draw 2 from the result data frame, divide those by 2, store the answer to that in a new column called av, for average. Run that. No mess ups. So once again, let's just type out result and look at the whole data frame. And what we see is that we have draw 1, draw 2, and the average. Because the math is easy, 12 plus 13 is 25. 25 divided by 2 is 12 and a half. Yeah, what you got, Samuel? Okay, so it's not reading. This is a data frame. Yeah, so your data frame command didn't work. See how it's still a numerical, just a list of numerical values. Yeah, you must have typed that and then you didn't run it. So now, when you do the rest of this, it should, well, why are you doing structure? Don't do structure. You want to do, this is calculating the average. What you want to do is you want the $, average here. So you're making a new column in result, and you're putting this stuff in there. Now you want to just see result. Yeah, there you go. So in that case, so what Samuel was trying to do is he put str result out here instead of result $av, and then asking it to do that. Since this is actually a mathematical operation, it's not going to give you the structure of a mathematical operation. And also, str result shouldn't have anything after it. So you're just doing wonky syntax. So one of the things you should do while you're coding, while you're scripting, is pay attention to the details of what you're coding. And oftentimes I'll do it line by line when I'm building a script so that I know, okay, this line works. Okay, then I can move on to the next line. Yeah, what you got?
This is not a huge deal, but so I ran average AVE first, and then I realized that I wanted to change it to AVG average because that makes more sense in my head.
Yep.
How do I get rid of one of them?
You can
Is there
do
a way?
you can do it with a subsetting code, but for right now we don't.
Okay.
You don't need to
guys
really
said
worry
it
about it.
doesn't.
Yeah, you can. You can do the kind of subsetting that we did with the COVID data, which we really blew through. We'll talk about subsetting later. But yeah, just don't worry about it. But now you can do either AVE or AVG. It doesn't really matter. The other thing you can do is just go back up to the draw and just rerun the code and get rid of one of your averaging lines. For small data sets like this, it's easy. You don't have to, yeah, you can just, it automatically forwards. So you don't have to move it to the next code. Does that work?
Yeah.
Okay, great. Awesome. Okay. So we have the result. Now what we want to know is what is the average of the averages? An average of averages is usually referred to as a grand mean. So we're going to do grand mean. And it is the mean of the column result $average. And because you assigned it, it runs the code, but it doesn't tell you what the grand mean is. But you can get it by just typing in grand mean. And you see that the grand mean here for my data set is 7.55, which is pretty close to 7, which is what you would expect of a population, of a distribution of sample means. The mean of that distribution of sample means should be close to the population mean. We can also get the standard deviation of the grand mean by creating that. The standard deviation of this distribution of sample means, rather. And once again, if we run that, it should give us what the standard deviation is. Now we can make a simple histogram of this. So all I'm doing here is I'm naming something histo, which is going to be a histogram. The histogram is of the data in result $av, the average column of your data frame, breaks it into 14 different bins to put the data into, and the bins vary from 1 to 13 because those are the values of the cards that we have. So xlim tells you what the x limits are on your x variable. So it's a command to make a histogram. Here's the data. Here's how we want the x-axis broken up, and these are the values for the beginning and the end of the x-axis. That's all it does. Run that, and then type in its name, and you should get a histogram. And I have an error message. Oh, I didn't put an equal sign in where I needed it. This is the bane of my existence, is typing. So now it's given us a histogram. Yeah. Let me put up the green thing if you've got a histogram.
So I forgot my backpack.
Yeah. So you need an equal sign after xlim.
After xlim.
Yep. And then you need to put a C out in front of that.
Equals. And then out in front of the x.
Nope, in front of the parentheses. concatenate. You're concatenating 1 to 13. Now it should run. I'll just run that line and then call it up. Oh, wait, still giving you an error message. Breaks. There's an S in breaks.
Okay, now I
And you've got a histogram.
just,
You got it.
oh, I don't even have to call it; it'll automatically pop it up. I don't have to ask it to.
You probably accidentally hit the run button twice. Okay, everybody have a histogram? All right. So you just replicated the sampling that you did on your homework assignment. You've just now done it on the computer. So now what do we want to do? The computer-based portion of the card assignment will not be due on Monday. It will be due on Wednesday because we are going to finish this because we have like 2 minutes left and we can't really do the next thing. What we're next going to do is we're going to start ramping this thing up and making bigger and bigger populations and drawing more and more cards. And then we're going to do some things where we all kind of automate that process. And we're also going to calculate the empirical rule, and we're going to graph the empirical rule on these histograms. And that's going to take more time than we have in the next 2 minutes. So save this script, because this is where we will start next time. So on Monday, we will be back in here again. Monday, first thing you want to do is you want to open up the script and run the script down to the point where it's at right now so that we're ready to go at the beginning of class. And then we will finish this little exercise on Monday because we'll have plenty of time to do it because I won't be talking about the central limit theorem at the beginning of it. On your cards, on your note things, green one, what went well today, pink one, what didn't go so well, and turn those into me as you leave. Be sure and wipe down your surfaces so that the next group of people come into a nice clean room. And enjoy your weekend. How's school going? Is it weird still? Or is it starting to normalize? Okay. You don't sound like you like that, that it's normalized. Did I save mine? I did save mine. Okay.